section 13.3, talking about special right triangles. And in our last video, we talked about the Pythagorean theorem and how that works, and looked at a few examples. And again, that's something that most of you have probably seen before, probably something that's not super difficult for you. And so we're going to begin to get into some special right triangles. The first of those is what we call a 45, 45, 90 rectangle. Triangle. And basically in a 45, 45, 90 right triangle, it says that you have two angles that are 45 degrees, which means that it's an isosceles right triangle. And the length of your two legs are the same, with your hypotenuse being that number times the square root of 2. Okay? So we could go through and we could actually, assuming that two of our sides are 1, we could go through and solve and use the Pythagorean theorem, and we would find that the hypotenuse is the square root of 2, which is bigger than the 1. And so that would make some sense. And again, that probably doesn't mean a lot to you from the standpoint of knowing that exact distance. But that is an exact number, because the square root of 2 is irrational, and so that's how we're going to be able to find that. Now, in general, if the side length is some number s, then the hypotenuse is s times the square root of 2. Okay, based off the Pythagorean theorem, that's what we're going to get every single time. And we could go through and prove that. Again, we're not going to, just for the sake of your sanity and the sake of time, we're not going to go through and actually prove to you that's the case, but it is. So I'll give you a quick example. It's a sports example, just because the one that I think of right away. In baseball, you have from first base to second base to third base to home plate forms a square. And the length from home plate to first base, which is here, is 90 feet. Okay? And so one of the things that has to happen a lot of times is a catcher here at home plate throws down to second base, which is at the top of this square. And so sometimes if a catcher wants to work on making that throw, they have to figure out, well, how far is that? Well, this length from home to first is 90 feet. From first to second is also 90 feet. And so based on that, at first base we have a right triangle, or we have a right angle. And so this length from home to second base must be 90 square roots of 2 as that distance. Now, you may look at that and go, well, what does that mean? I don't understand how far 90 square roots of 2 is. Well, you could change that to a decimal, and it's 120, I think it's 127.3 feet, maybe 128.3, something like that. But from an exact measurement, it's 90 square roots of 2 feet. If you wanted to know the approximation, again, you can punch that in the calculator. Again, it's either 127.3 or 128.3. I don't remember right off the top of my head. But that would be the exact measurement. And so we know that based off this 45, 45, 90 triangle. There's some other instances you could use. That's just one that's kind of common that I typically think about. We also have another special right triangle. And it's what we call a 30, 60, 90 right triangle. So a 30, 60, 90 triangle actually comes from an equilateral right triangle, where each angle measurement is 30 degrees. And when we have a 30, 60, 90 triangle, we have one angle that's 30 degrees, one angle that's 60, one angle that's 90, obviously. And Your side lengths, this shorter side, we'll call it S, is going to be kind of our base side that we start with, and everything else is kind of based off of that number. The hypotenuse is 2 times that shorter side, or we're going to call 2S. You can see that over here to the right. And then the other leg length, this one that is the altitude of this equilateral triangle, is S times the square root of 3. Okay, so again, we could go through and prove that. I've actually got notes where I was going to do that for you, but I just think that'll be a little more confusing for you than is necessary. And so I would recommend that you just memorize this, that in a 30, 60, 90 triangle, S is the shortest side. It is the side across from or opposite of the 30-degree angle. The 2S is your hypotenuse. That's across from the 90-degree angle. And then the S square root of 3 is across from your 60-degree angle, or opposite to the 60-degree angle. And so if you were to take each of those angle measurements and draw an arrow out across to the other side, that's the opposite side that we're talking about. The 2S is the bigger length. It's the hypotenuse. S is the shortest side. It's across from the smallest angle. And then 60-degree angle is across from the S square root of 3. And that's what all of this stuff down here at the bottom says. You can see all of that. So, if we have a triangle with side lengths of A, B, and C, such that C squared is equal to A squared plus B squared, then triangle ABC is a right triangle with the right angle opposite the side length of C. Basically, this says that the opposite of the Pythagorean theorem also works, the converse of it. So we say that the Pythagorean theorem says that in a right triangle, A squared plus B squared equals C squared. Well, this converse of this theorem says that if this is true, then that implies that there is a right triangle. And you may think, well, that's obvious. Well, not always. Sometimes we have theorems that do work one direction and the other direction very easily. Sometimes we don't. Because this one says, if it's a right triangle, A squared plus B squared equals C squared. The converse says, if A squared plus B squared equals C squared, then it must be a right triangle. Sometimes there may be a situation where you have some statement, some equation that is true, but that does not necessarily mean the triangle is right, or whatever that original statement was. But in this case, the converse of the Pythagorean theorem does work. Just like my example in the previous video about the builder, if he stretches out a 3-foot piece of string and a 4-foot piece of string and then connects that with a 5-foot piece of string, well, then he has absolutely formed a right triangle here in that corner. And so he can know that for a fact and not have to say, well, that part of it worked out. Is that a right triangle? He can know for sure, because the converse of the Pythagorean theorem says that if this is true, if that works, then that is a right triangle. Okay? So what we're going to do here is we're going to look at the side lengths. And it says we're going to determine if the following can be the lengths of a right triangle. So what we need to do is we need to figure out if A squared plus B squared is equal to C squared. Remember, C is always your longest length. Okay? So in the first one, if we take 51 squared plus 68 squared, we want to know, is that going to be equal to 85 squared? If it is, then we have a right triangle. If it's not, then we just say no, it's not. And so, again, using some calculations here, 51 squared is 2,601 plus 68 squared, which is 4,624. And again, we want to know, is that going to be equal to 85 squared? Well, 85 squared is 7,225. And when you add the 4,624 plus the 2,601, you do get 7,225, and that's equal to 7,225. And so, because those two are equal, then we would say yes, those side lengths do form a right triangle. And so, again, I've written where all this stuff's going to show up, so bear with me here. So, the PowerPoint slide doesn't actually work it all out. I've worked it all out for you. You can see that. And see that the answer is yes, that one does work. Now, if you have questions about that, again, let me know. Look at the next one. So first of all, we need to understand that the square root of 13 is bigger than 2 and 3. So that square root of 13 would be our C side. So we want to know, does 2 squared plus 3 squared equal the square root of 13 squared? Well, 2 squared is 4. 3 squared is 9. The square root of 13 squared is 13. And 4 plus 9 is 13, so that equals 13. And so again, yes, these are the side lengths of a right triangle. So again, you can see it pops up there as yes. And then, because I've talked about this a good bit already, you can probably answer part C pretty easily and find out that the answer is no. But assuming that you don't, because this is a 3-4-7 triangle, not 3-4-5, and so you probably could recognize that and say, oh, well, no, that's not a 3-4-5, it's a 3-4-7. And so it's not a right triangle. But assuming you don't know that, let's plug all these into the Pythagorean theorem. And again, we want to know, is that going to be equal? Well, 3 squared we know is 9. 4 squared is 16. We're wanting to know, is that going to be equal to 49? You can obviously see it's not. 9 plus 16 is 25. That is not equal to 49. And so no, this is not the side lengths of a right triangle. So there you go. If you have questions about that one, let me know. Be glad to answer any questions you have. Now, let's talk about how the distance formula, because this is something that is quite useful here. The distance formula is a formula that you use in college algebra. It is something that is pretty commonly used, and it is derived from the Pythagorean theorem. So if you're looking at the distance between 2 points, we'll say point C here and point D. Well, in a coordinate plane, you could form a right triangle, right? Where you come down and you come across to where you form a right angle that you see here. And then using the Pythagorean theorem, you could say 3 squared plus 4 squared is equal to this length, which in this case, again, it's a 3-4-5 triangle. You would get a length of 5. Well, that distance formula that we're going to talk about in just a minute comes from this idea. Because if you think about, well, how do I actually do this? What am I doing when I find the length of this hypotenuse? Well, you're finding the length from here to here. So we find that length by subtracting those numbers and taking the absolute value. And then you're finding the length from here to here, this length. And again, you find that by subtracting those numbers and taking the absolute value. Oh. And then you square both of those, and that should give you the c squared, this value squared. But in a formula, we don't want to square it. We don't want to have to square the number, so we take the square root. And so what we find out is that the square root of this difference in my x values from, in this case, 2 to 6, so we'll call it x sub 2 minus x sub 1, and then squaring that plus the difference in the y values, which is y sub 2 minus y sub 1, ooh, it's not a very good one, squared. This part is your a squared plus b squared equals the c squared, but to get the c by itself, we take the square root. And so this ends up being our distance formula. Now, let me kind of walk you through, without the numbers, how this would work. So let's do this. I'd like to do one without that picture there, but we'll use this picture. So let's call this point x sub 1, y sub 1. Call this point x sub 2, y sub 2. And then if we're wanting to find the distance between those based on the right triangle, this c has to be x sub 2, because you would go right this value. And then the y value is this y sub 1, right? Because you would just go up some amount to get here. And so those are going to be the order pairs that we use to kind of prove this. And so if you take your distance formula, you take the Pythagorean theorem, well, we want to take this value, the difference in the x's, and square it. That's where this part comes from. And then we want to take the difference in the y values, which is this, and square it. So that's where this comes from. And then that's equal to this AB, this length squared. And then to undo the square, you take the square root, and which is where the whole square root came from. And so again, not going to walk you through every little detail of that, but I do think it's important you see that the Pythagorean theorem helps us get to the distance formula, which is then going to help us solve problems as we move forward. We're going to stop this video here. We've got one more video that I think will cover the end of this section before getting into section 3.4. We'll deal with the distance formula in more detail in the next video.